everyone. I think we'll probably make a start now, if that's okay. So welcome to the blue room of this showcase. If you're not aware already, this is just a drop-in session. So feel free to flick between this blue room and the red room. I've put the link to the red room in the chat if you would like to switch between. So just a rough overview of what we'll be looking at. Is sort of resilient systems, nature-based solutions, and they'll be structured in a 7-minute talk followed by a Q&A session. So we ask that if you're able to raise your hand only during the Q&A session, or you can post it in the Q&A tab if you have any questions, and we can go from there. So without further ado, we will start with managing resilient systems. And I believe we have Adrian presenting today from Arup. So welcome, Adrian.
Hi, you can hear me? Just to check.
Yep, we can hear you.
Right.
Yeah.
Okay, fine. Okay, and I understand you're going to drive the slides for me. Is that right?
Yeah. Yes.
Cool.
So,
perfect. So if you want to move on to the next one, that'd be good. Let's get the one ready. Oh, okay. I think okay. Right. Obviously, I have to click something to make this work, don't I? To sync it up. Oh dear. Why am I not? I'm not seeing your slides, unfortunately.
Okay.
No, I think that might just be me because it says it's me. You've moved to slide 4, and I'm not seeing it for some reason.
Does it say sync to presenter?
Yes,
on your
and I'm clicking. Yeah, I'm clicking on that, and it's not doing anything.
Oh. Okay. Bear with me a moment.
I don't know. I don't know what the other attendees are looking at.
Sure. Sorry, Tom, can I call on you just to see if you can see the slides okay?
If it's just me, then I can drive it. We can do it separately.
I can see.
You can.
Tom
Okay.
can, okay.
Okay. So
I've got La Mesa water treatment plant.
Fine. Okay. It's something to do with my machine then. So I'll work it round. Fine. Okay. So after that slight technical hitch, just quick introduction. So yeah, my name is Adrian Marsden. I'm based in Manila. I've been here for the last 12 or so years now, working for Arup on a range of water and wastewater treatment projects. The session was presented the other day by my colleague Mervick. So yeah, we're going to talk a little bit about the La Mesa treatment plant project we've worked on recently. And I see from some of the attendees, we've got a couple of attendees from the client team at Minelad. So I'm sure if you've got any other questions, feel free to ask or contribute as we're doing the questions. So if you'd like to just move on to the next slide for me. Then what you should be seeing now is a quick overview of Arup. So for those that haven't come across Arup before, it's a global engineering consultancy. We have teams all around the world in 90 or I think 40 or so countries. And in Manila, we've had a presence here for the last 25, 30 years. And the last 10 of those, we've been working on a range of water treatment projects. And as you can probably tell, I'm originally from the UK. And we've tended to share our knowledge between the different locations we work in quite extensively. And if you move on to the next one. So, and our whole principle of what we're trying to do here is work with all of the factors of the water cycle, and where we can actually build net gain into the projects that we're working on, managing the whole of the supply, flooding, water quality issues for a holistic and integrated approach. If we slide on to the next one. So let's just talk about this particular project itself. So the image you're seeing on screen is the inlet to the treatment plant during one one sort of typhoon event a couple of years ago. And as you can see from the quality of water, there's a lot of turbidity in that water. And just to give an illustration, the La Mesa treatment plant, and I'll go into a bit more on this in a minute, the La Mesa treatment plant was built about 40 years ago. And at the time, they weren't suffering too severe extreme events, but more recently those events have got worse, and turbidity is probably the biggest factor. Another factor that we've had to deal with is also just a better understanding of seismic conditions in the area and what that means for the resilience of the infrastructure. If you slide on to the next one for me. So the image you're seeing on the right is just a quick overview of part of the plant. So La Mesa is the biggest water treatment plant in Metro Manila, handles about 1,500 megalitres a day of treatment capacity. Minelad, the client, handles basically half of the population of Metro Manila, and that's an urban area of anywhere between 14 and 20 million, depending on how you draw the line. And La Mesa is the biggest treatment plant in their infrastructure, handling roughly half of their treatment capacity. So a major piece of infrastructure. As I said, it receives a wide range of inlet water conditions, and that range has changed quite significantly recently. Just to put it in context, the average turbidity would typically be about 20 NTU, commonly getting up to sort of 200-300 during storm events. But what's been seen more recently is that turbidity has been going up to 800 and then to 2000, and the frequency of those events has been getting more common. And unfortunately, when that's happened, obviously the plant can't cope with it, and they've not been able to supply the water to the customers. So that's been a big problem. And when we came to this plant, also there was no sludge handling system, no significant sludge handling system on the plant, also constraining it. And I touched on the seismic conditions. Metro Manila sits in a very active seismic region, and when the plant was designed, the understanding of the seismic design factors was very different to what it is now. So in the event that there is a seismic event, and we'd predict it'd be quite large events here, then the risk is that the treatment plant is damaged and then can't supply water. So with that better understanding, something had to be done about that. So we've been working on a project or we've just finished a project to improve resilience of the plant. So if you can move on to the next slide. So the process we adopted was fairly conventional, but started off by auditing the plant, looking in detail about the existing condition of the structures, the treatment process. And then we moved into developing a process and structural upgrade to improve the capacity of the plant in terms of its ability to handle the range of water quality conditions and also its seismic resilience. The seismic resilience component involved strengthening the concrete tanks, adding structural retrofit to them. And the process upgrade involved installing lamella settlers, altering the way in which the filters worked, and then building a sludge system. In doing that, we were able to maximise our opportunities for some waste and carbon emission management. The treatment plant was actually covered in the end by solar panels, which cuts the use. And in doing the concept design of a plant, which is where we came in doing the concept design of a plant, we were able to look at balancing some of the risks of how to size the turbidity handling so as not to overdo it, to give it the ability to treat what the maximum conditions were, but not to have too much plant that was sitting there. So taking effectively a risk-based approach to having sufficient capacity during the extreme events, but maximising the infrastructure without wasting the infrastructure, and therefore actually not having plant that sits there most of the year not being used and then doesn't work when it's really critically needed in an event that comes along. There's a little bit more detail behind that, but simplistically it meant that we were holding sludge in different parts of the process at the right best time. So you can move on to the next slide. So as part of that, and the way we did the design and where we specified the design, we were able to recover about 9 megalitres a day from the backwash system. So as that's not being wasted, that now can be put into and used as part of the supply. The solar system and also some of the efficiencies and way with the system has now been done has allowed power consumption to be reduced by about 50%, and also reduces the chemical consumption by about 15% as well, due to the efficiency of the way the process is now able to work, and with the addition of the lamellas and the filters. And we estimate that this setup will saves around 650 tonnes of carbon emissions per year. Just also to illustrate, the Philippines still has about 60% fossil fuel generation due to the way the infrastructure here is set up and the growth of the economy. That percentage is going to be very high for a very long time. So anything we can do to reduce energy use is beneficial. And if you would just like to slide on to the next one for me. So yeah, hopefully we've just sort of summarised a little bit about the treatment plant. The image you're seeing on screen at the moment is looking over the new sludge system up through a couple of the lagoons that remain, and the basins are up in the top corner. And just to illustrate how this was done, and if you could just push it on to get the little FIDIC image to come up. if that comes up. The project won an award at the FIDIC Users Awards last year for the best project implementation using the form of contracts. So very much transferring knowledge that we've gained from all around the world into how we deliver these projects, and in this case, the complications of managing improvements on the 12 basins and keeping everything live while we're delivering the project. I think that's probably a summary of where I am.
Great, thank you very much. So now what we're going to do is sort of open it up for the Q&A. Again, if anyone has any questions, please raise your hand or put them in the Q&A tab. And also, if you're able just to say your name and where you're from as well, that would be a great help, just to give us more of an idea. If not, I think we've had some questions that were submitted earlier. We can move on. So one of the questions we had was, what are the challenges of intervening existing critical infrastructure?
Okay, quite significant. So, I mean, maybe just to illustrate, but just describe that a little bit more. So obviously this is a major treatment plant. I can't remember exactly the number of people it's supplying, but yeah, if it's half of the service area, it's a number of millions of people's of assets. So yeah, we have to be very careful about managing it. So the first and most important thing was we had to make sure that in doing the upgrade work, we were able to keep the plant operating and keep producing the water. One of the things we did for that was actually sort of, should we say, manage the number of units that could be taken out at different times of year. So in planning the project, we said we planned it such that the contractor was allowed to work on, I think it was 2 sedimentation basins, maybe 3, during the better water quality periods of the year, and during the worst water quality, that was limited to 1. So the sequencing was done that way to manage what they could intervene in, minimise the risk that it would stop the plant operating at any point. And I think all through the construction process, they maintained the output required. So yeah, I think it was more of a very careful planning and sequencing. And there were some changes during the project, and there were some limitations that had to be applied. But yeah, it was delivered. It was delivered. Yeah.
On the other questions we had, what would you say are usually the challenges to ensure 24-hour water services? Is it purely technical, or is it a priority issue?
That would be, I guess, from a treatment plant capacity, it's primarily a technical issue of what can you keep running, how do you run it most effectively and efficiently, and from our perspective, helping or designing a project that, as I said before, it's about the planning of those interventions, what's allowed to be planned, and how do you do that effectively, looking at the relevant risks. From a client side perspective, their goal is to maintain 24-hour supply through the whole of their service area, and in general, they've been able to do that. There've been occasional periods due to normally major climatic events, storms and things, where that has been constrained. But the goal, that's then it's been managed through, I guess, it is prioritization of supply, making sure everyone's got water, but there may be limitations in the time. And I think it was 2019 in Metro Manila, the other concessionaire had to rotate supplies because they were short, and there was a limitation in the upstream supply capacity when during the summer period. Yeah, so they had to rotate and prioritize the supply to keep everyone being supplied by water. But it's certainly a big challenge with infrastructure that's limited and significant, as I say, rapid urban growth. Yeah.
Thank you. So I've got a final question. So for the case of high turbidity events, how do you manage the trade-offs?
Yeah, so to explain a little bit more about what we did here. So instead of designing the plant to be able to remove all of the sludge, as quickly all of the time. The trade-off was a balancing act between looking at how much capacity could be maximised from the basins without compromising the treated water capacity, and then how big the sludge treatment system, which in this case compresses belt thickeners, how big they would need to be. And there's a cost balance to that, and there's a practical balance thing, because I said through the talk, the cost balance was, do you put in 40 treatment units or 10, and keep the 10 used most efficiently? And the practical balance is not having those 30 units sitting there that are only used 2 days a year, because when they want them, they won't be wanted. So it was a trade-off, and then working with the client team so they appreciate that how much sludge is going to get caught in these basins for how long, and how long it's going to take to get back down to the normal operational level, because that's another risk question. And I don't know, maybe over time that's going to have to be looked at again, because as the changes in storms happen, the frequency of those storms, if we get 2 or 3 stacking up on top of each other, and that happens commonly, maybe a bit more resilience will need to be put in. So maybe future flexibility is the way to put it. Constantly looking and revising. One other advantage of having done a project like this is the plant is much better automated and instrumented. So there should be a lot better data available on which to make future looking decisions as well. And that's just a function of moving on 40 years and having the ability to put more instrumentation and control systems in. And that should hopefully allow a bit more interpretation to be done. Yeah.
Great. Thank you very much. Thank you for joining us. Wonderful. And so we've got a couple minutes before the next session, unless Tom would like to get started. Again, people can always drop in and out between the rooms. But yeah, thank you again, Adrian.
You're welcome. Thank you.
Okay, so we have Tom Godfrey leading our next session, starting on nature-based solutions and the restoration of salt marsh using a circular economy-based model. So Tom, it'll be over to you.
Thanks, Maya. Good morning, good afternoon, everybody. My name's Tom Godfrey. I work for Earthchange, which is a division of land and water. If you go to the next slide. Okay, so it's Land and Water is it's an environmental engineering company. We work predominantly in the UK, but we respond to national emergencies, things like Cobra when large areas of the UK are flooded. The Environment Agency will call upon us to say, what the hell do we do? How do we sort out Somerset, an area of the UK? We work for all sorts of different people in terms of keeping the canal system of the UK open. We create docks and all sorts of different things. So, but Earthchange itself is a division of Land and Water, and we deliver. Basically, what we do is we improve the quality of water through creating high-value ecosystems, which are wetlands, woodlands, wildflower meadows, salt marshes, that side of things. Okay, next slide, please. So we have a thing called a no regret strategy, because in the UK, obviously, we're a pretty small country with quite a few people, and so food security is really, really important. And although there needs to be a lot of rebalancing of nature and the restoration of these different high value ecosystems, that it can't really be done at the cost of food, so of arable production, of farming, and everything else. And so where we tend to focus on to deliver these this natural capital benefits is areas that wouldn't be used for anything else. So that's closed landfill sites, where intertidal areas, subtidal areas, and where we create different habitats there for sequestration of carbon or biodiversity net gain, various different things. And we do everything from we do the whole project. So we work in partnerships with different universities to research and to ensure that much of our work is effective and efficient. We deliver it, we finance it, and we obviously will monitor it and maintain it once it's being done. Okay, next slide, please. So what I want to talk to you about today is an invention of Land and Waters called the Salt Marsh Restoration Drag Box, which has, we think, fundamentally changed the way in which salt marshes can be restored. Heretofore, there's been managed realignment and also a pumping of water, of sediment onto the land to create salt marshes. This drag box now allows us to go into more difficult areas to access and to pull sediment up to create salt marsh. And so many salt marshes in the UK, over 60%, have been lost over the last 100 years. It's an incredibly, as you'll see, is an incredibly efficient media. Everything from flood, well, really from storm damage and flood prevention or mitigation to various biodiverse benefits. Our approach is basically the dredgers come along, they dump the sediment, and we then pull that sediment up to the shore, the top of the shore, and which allows us then to create the salt marsh, and where the salt marsh then self-seeds. Thank you very much. Next slide. Here you can see how it's a small area. It's only half a hectare, but this was the first time that the drag box has actually been used. And you can see just the end of it in the background there, it being dragged between the winch and the pontoon at sea. But this is the finished area, which has been pulled up to the edge of the wetland, the salt marsh. And I'm happy to report 4 months later, we're now seeing the first green shoots of recovery there, of the salt marsh actually beginning to self-populate itself. Okay, next slide, please. Okay, so just within the context of this, I've put here a map of New York in the US, and I do that only because it's roughly 50,000 square miles, and that's how much salt marsh has been lost globally in the last 100 years. Within the context of the UK, we've lost 22,000 hectares, quite a small amount, but we are very small. But the benefits here to the right of the actual of salt marsh restoration is there. It's interesting to note that maybe some of you will know this, but 75% of marine life spends some of its time in wetlands. So whether that's freshwater or saltwater wetlands, whether it's laying their eggs, whether it's growing their young, whatever it happens to be, there's nitrate and phosphate absorption. There's incredible. Its CO2 absorption is second almost to none, and there's all sorts of different there's different mental health benefits and other things which are delivered for salt marsh. And so we are we are a company which is driven through innovation around automation. We are looking to scale, and we think we've got different solutions to problems around where land meets water, basically. One of the innovations that we've just tested in Wales is a seagrass planter, and so we've just automated the planting of seagrass, which instead of doing it in the UK, most of it's being done by hand in some way, shape or form. We can now do it by seagrass plate, and that allows us to plant up to 2,500 sacks of seagrass a day, which is substantially faster than anything is at the moment. Yeah, so that's it. So we're basically, as a company, we're looking to create these high value ecosystems where land meets water on useless land, helping local communities and governments and companies offset the nitrates and phosphate use, as well as create biodiversity net gain. Thank you very much.
Great, thank you very much, Tom. Again, yes, if anyone has any questions, please raise your hand, pop them in the chat. Okay, here's a question from Steph. I'll just give Steph access.
Hi, Tom. I don't know if here I am off camera. Thanks so much. That was really interesting. A couple of questions, but I'll just start with one. Is there much competition for the land that you're trying to use? So if you're approaching, I don't know who your kind of target audience is, it town planners, that sort of thing. Are there other people trying to use the land that you'd like to use for different?
No, no, and that's the great thing, the government is the intertidal area. Nobody's particularly interested in it because it's covered with the sea. It comes in and out over it. Closed landfills. No one's particularly interested in closed landfills, and well, except for the for people like Suez and Veolia, who are trying to manage the leachates coming out of it and look after it. And so therefore, if you can create, you can optimize their biodiversity or their natural capital potential there. It's all just a win-win, basically.
Amazing, thanks. And also, as this technology as a flood defence, how do you see it interacting with like other more traditional forms of flood defence? Can it replace, or is it alongside kind of concrete or traditional?
Yeah, so there's the biggest form of salt marsh creation is managed realignment, where people knock holes in walls and sea defences and let it come through, and a salt marsh is created. There is coastal squeeze, where where salt marshes, or there's actually, as sea level rises and different things, that becomes more and more difficult to create salt marshes. But salt marshes work very much in tandem with hard sea defenses, or can be a soft sea defense themselves. But no, they will attenuate waves. They won't do that. They are a bit like canoes. they will slow down storms and everything, but they won't stop storms, basically. But they'll make hard sea defenses last for a lot longer than they would otherwise do, because the power of the waves has been taken away. So that's their main role. They can't claim, as amazing and as powerful as they are, they cannot claim to be able to stop the sea. No.
Sorry, Steph, you're on mute.
Sorry, thank you. Yeah, no, I think we're definitely guilty of thinking of hard and fast, quick solutions that can solve all your problems. But with water issues, it does feel like you need a range of solutions, especially if you want to be doing other things like enhancing biodiversity and. Yeah.
Well, the developer now in the UK, there's I don't know, globally, there's developers now can't build houses unless they offset in 72 areas of the country, so offset nitrates and phosphates. In some areas of the country, they can't build houses unless they offset water. So there's water neutral solutions. And so we have to begin to think more creatively about how we put stuff back into the land that we take out. And so there is that's not to say that offsetting is 10% of the solution. Most of all this is just consumer change, but nature-based solutions do have a role to play in preserving our planet, and that's what we tried to do in areas that can't be used for anything else, basically.
Thank you. So I'll let someone else take the floor. I'm hogging the.
If there are any other questions, but if not, we do have the question of just asking if there are any limits to nature-based solutions and where they could be implemented.
So I don't think. I think we have to. The government, I think, has to think really carefully about nature-based solutions, because they're. With development has changed, and there is, and what they allow and what they don't allow. But our coast, there's in wetlands and just within the UK, in wetlands and so both freshwater and saltwater, there's probably 100,000, 120,000 hectares that can be reclaimed, that wouldn't be used, for much else. In the UK, there's 22,000 closed landfill sites, which again, are generally covered in grass and scrub because they've been poorly reinstated. And I just think, obviously our issues are very different from other countries around the world, but people just have to think carefully about what they can and can't be done with land, and what is the best use of land. But then how do we create biodiversity, and how do we look to offset the causes, the consequences of our actions? So I would say that.
And sort of off the back of that, then, how scalable is your particular approach?
Yeah, it is very scalable. I mean, there is, as I was saying, is at 120,000 hectares in the UK. There is, again, we're a very small, crowded island. I mean, most other countries don't have the issues that we do, but there's probably, again, the same amount of land, in closed landfill sites, which again is, is quite small compared to Amazon forests and whatever else. But it's something that the UK can do for itself, and more crowded countries can look at ways in which you can optimize the use of a limited resource, which in the UK is land.
Great, thank you. So I don't think we have any more questions at the moment, but I'm sure people can reach out to you at a later date if they have any questions in the meantime.
Lovely, thanks so much.
Thanks, Tom. Bye. So we are running a little bit ahead of time. So what we will do is just pause before we move on to the next part of nature-based solutions. It means it will allow those from the red room to join if they would like to. So we'll probably get started in the next 5-10 minutes. Thanks. Yeah, I think we can look at making a start on our next slot, if that's okay with Richard. So again, continuing with nature-based solutions, and we have Richard Noakes speaking up today on a natural infrastructure. So welcome, Richard.
Thank you, and hello, everyone. I'm a technical director in our water team based in Cambridge, but with experience worldwide. I started my career about 40 years ago in rural water supply in East Africa, and I've been involved in all types of water development around the world since. Next slide, please. So today I'd like to showcase 2 project examples of how nature-based solutions can be used in different ways. My first example is from the islands of St. Lucia, where we took a nature-based solution approach to catchment management to improve a river used for water supply. In my second example, I'd like to show you how we've used constructed wetlands in Derbyshire for Severn Trent water as preliminary treatment for potable water. The next slide, please. First, just a little bit about MacDonald. We're a global engineering, management and development consultancy with about 18,000 staff spread around the world across about 135 countries. So alongside environment, buildings and structures, energy, transport and international development, our water sector has about 100 years of history supporting our clients to manage and store, distribute water to communities and within the environment. It's part of our ethos that we consider social outcomes in all that we do. The next slide, please. So why use nature-based solutions, and what are they in this context? Well, they're measures that work with nature to give innovative approaches that regenerate areas affected by human activities. They restore key ecological functions that improve people's quality of life. They will probably contribute to enhanced biodiversity net gain. So they cover a wide range of interventions, approaches and techniques, including catchment management, natural flood management, urban blue-green network, green buildings, etc. And they provide ecological restoration in urban environments, and they help to connect people with nature. And they can complement traditional engineering approaches or they can be employed in their own right. But the key thing about nature-based solutions is that they can have multiple co-benefits. For example, they can relieve pressure on storm overflows, which is something highly relevant in the UK at the moment. And using nature-based solutions instead of grey infrastructure is something that is in its infancy, and the industry is learning and needs to build confidence in these solutions. In Mott, we follow a 6-step framework to apply these systems, and it's all about maximising the co-benefits of the solutions and gaining more confidence about their performance and cost. We look at the multiple outcomes that can be achieved from nature-based solutions. There might be regulatory requirements or organisational KPIs like biodiversity net gain, net zero, etc. A systems thinking approach is required here, as stakeholder engagement is going to be needed to get buy-in from partnerships. The solutions may well accrue to various stakeholder groups, so a blended finance approach might be suitable. If you could move to the next slide, please. May require a couple of clicks. So, Lucia, Port View is the international entry point for St Lucia, and there are plans to expand the nearby airport. The economy is quite agriculturally based, but it's growing. There's a growing tourism manufacturing industry. So to thrive, they all need access to more good quality drinking water. Problem is that the supply comes from the local river, which has a small catchment, and during the dry season, flows drop, causing a deficit. On top of that, there is a significant water quality problem. Heavy rains cause turbidity, exacerbated by agricultural practices along the river, causes soil erosion and slope instability. The intakes often get blocked. So upgrading the treatment plant might be an option, but unfortunately, it's expensive and would not be sustainable. So the St Lucia Water Management Agency wanted to develop a watershed management plan, aiming to investigate the role that nature-based solutions could play in solving this problem. Next slide, please. Our approach preparing the watershed management plan was based on quantifying the benefits of different potential options over baseline water conditions. And that involved setting up a catchment plan model. To understand the root cause of turbidity in the river, we calibrated this model so it can simulate the movement of water and sediments across the catchment. We then modified the model to incorporate the effect of different nature-based solutions. So those range from changed land uses, improving farming practices, perhaps filter strips alongside the river, or wetlands to retain sediments, and protecting the banks from erosion. Finally, we discussed these findings with institutional and community stakeholders in a series of workshops. Each option was evaluated not only as a function of how effective it was, but also considering cost, socio-economic impact, and environmental impact, and any legal implications perhaps. And stakeholders were able to score the options for non-quantifiable factors and give their opinions about the relevance. So a multi-criteria assessment was then used to combine the inputs to rank the options. And the successful options were check dams, riverbank protection, and filter strips along the river network. And the implementation of those measures is now underway. Go to the next slide, please. Finally, by way of contrast, I wanted to make a quick mention of some constructed wetlands we have designed and installed on lagoons formed of old gravel pits adjacent to the River Trent in Derbyshire. Constructed wetlands are a floating matrix of polyethylene tubes, matting, mulch, and compost with plants that create a dense root mass specially chosen for their treatment performance. This forms part of a much larger Severn Trent green recovery programme to build a new water supply for the East Midlands within England, taking water from the River Trent, which is quite a polluted river and notoriously difficult to treat. So wetlands are being considered as a means of providing preliminary treatment as part of the treatment process, with the aim of reducing the load on the conventional treatment plants, therefore reducing its carbon impact, its energy use. The wetlands have recently been constructed, as you can see here, and they'll be brought into use early next year when the associated water treatment plant is commissioned. Thank you very much.
Great, thank you very much, Richard. Again, we'll just open it up to questions if anyone has anything to ask Richard at the moment. But nothing as of yet, I'm afraid. You might be glad for that, I don't know.
Yeah, perhaps I should add that using floating wetlands for water treatment is relatively innovative. They're quite widely used in wastewater treatment, but this is going to be one of the first instances there where they're used as part of the drinking water treatment process. So there's a lot of interest in how they do perform in reducing nitrogen in particular and ammonia.
So Martin's got a question, so Martin, over to you.
Yeah, thank you, Richard. Great presentation. I was just thinking around the skill sets required for nature-based solutions in different parts of the world. Obviously, they need to be locally tuned. What sense have you got in terms of how some of these ideas and systems are transferable? To what extent is that, or do they need to be sort of locally thought through?
Well, they do absolutely need to be locally based, and I think the St. Lucia example is quite a good one for that, because that example had to take account of particularly of local farming practices. So it had to work with local farmers to understand how, because they would be affected by whatever solution was chosen. So the idea was to create a solution which was kind of a win-win solution for both the farmers and for the water supply itself. So yeah, most definitely it does need a local approach. Some of the techniques themselves might be international in nature, but an understanding of the environment and the ecological and natural conditions within that environment are obviously part of that.
Thank you very much.
Great, thank you. We've also got another question from Kiri. So over to you, Kiri.
Thanks. Hi there. I'm in the British Embassy in Kazakhstan, and I'm also looking at wastewater treatment here because as an ex-Soviet country, a lot of their infrastructure is dilapidated, it's on its knees, and especially wastewater treatment plants, there's not enough around Kazakhstan, so a lot of water just gets dumped into sort of lakes and things. And the plants that they do have are kind of on their last knees and not working. But not only that, they have really high, strictly controlled regulation for wastewater, so it never gets reused, and there's a lot of water scarcity here. So adding up all these pieces together, like I see there's some opportunity to help and engage. And I was wondering if you, I don't know, have any experience of Central Asia or like ex-Soviet countries. What could be done on like nature-based solutions to maybe reuse this water in irrigation for farming or something like that? I haven't really formed a fully sort of a question, but I was just sort of thinking out loud, and as there was time to ask you questions, I could just fire away.
Yeah, well, it's a very good question, actually. I mean, I have some familiarity with conditions in some Eastern Europe countries, and I kind of recognise the situation you're describing, and I also know that sometimes water reuse regulations are very strict and can prevent the reuse of water. But there's a lot that can be done. The use of wetlands actually, it can be part of that solution, and particularly in polishing the quality of water that comes out of wastewater treatment plants. And it does sound as though there's some fairly serious reconstruction needed of the treatment plants themselves, but wetlands can play a very big part in that and help to polish that water quality. And we know that round the world, treated effluent is heavily used for irrigation, for carefully chosen plants and vegetables. So it definitely could be part of the solution. In some countries, that wastewater is, or the treated effluent is recycled by allowing it to filter back into aquifers in carefully measured situations, so that it can then be withdrawn at a different location, and by which time it will have a high quality. So yes, it can definitely play a part in those solutions, and water recycling is absolutely fundamental part of reducing water stress around the world. So I mean, by contrast, we're looking at some options within Oman where they wish to use recycled water for industrial processes, rather than expensive desalinated potable water. So it's a contrasting solution, but it's very viable, and it's something that's starting to happen.
Can I just clarify? Is that in energy, like in green hydrogen, that kind of process? Are they looking to recycle water and use it in green hydrogen production, or like other facilities?
That is a possibility, and specifically it was general industry. Sometimes that industry is general manufacturing, but it doesn't need possible quality water. So treated effluent is absolutely sufficient for that, but it can also be used for irrigating certain plants and crops. I mean, I choose Oman as an example because it is such an arid country and water is expensive. So all options for recycling water are being explored.
Thank you. That's really interesting. Yeah, definitely lots of food for thought here.
Yeah. Thanks. Yeah, it's just an interesting situation you have there in Kazakhstan.
Great, thank you. Now we actually have a coffee break, so we will be reconvening again at 8:35. So thank you again, Richard. And we'll see you all shortly. Thanks. Our next module will be looking at digital tools for resilience. And again, for anyone who's just joined, this is the Blue Room, and there's drop-in sessions, so you're able to flip between this one and the Red Room. There is a link in the chat. And also, just to let people know, we have the UKWP LinkedIn page, and we'll be posting sort of update and content from these meetings with DBT on there. So if you'd like to sort of give that a follow, that'd be amazing. So I'll hand over to you, Juan.
Thank you very much, Maya. Good morning, everybody. Good afternoon, wherever you are in the world, or good evening. I just going to talk about remote tools. In the last few years, we've been using in our company a lot of satellite images for engineering projects. They do have several advantages. One is frequency of data. You've got periodically new data covering large areas, and also maybe remote accessible areas. And one of the problems it used to be price. It used to be very expensive, but the price is going down as more people using it. So I'm going to show you a couple of examples. We've got more. We've got very unusual applications like forecasting of dengue outbreaks in some places in Southeast Asia, or the ones that you're going to see today. So I think there are a lot of applications that can be done, and a lot of information, especially related with soil moisture and the groundwater recharge, that can be very, very useful for water applications. Our organization, it's very small compared to some of the organizations we've seen here. We have about 300 employees, and we are very specialized in the water and energy sector. We work all over the world, and we are a particular company because we need to reinvest all our profits into hydraulic research. We used to be part of the government. We got privatized in the 1980s, and right now, all the profits we make, we need to reinvest them into hydraulic research. So some of the tools you are going to see today are actually the product of reinvesting these profits into some useful tools for the hydraulic industry. So I'm going to start with a case called DAMSat. DAMSat is a tool that we've created for helping managers of dams, water or tailing dams for the mining industry, to increase the safety of those dams. Well, we are trying to avoid this situation like this, or at least mitigate the impact that this can be happen. This is the Brumadinho Dam in Brazil. Happened quite recently, I think in 2019. It caused the death of 270 people, mainly workers around the area. And that was a terrible disaster, also not only in the loss of life, but from environment point of view, because the waters that were stored in that dam, they were quite polluted. And it also actually caused a terrible impact in the company numbers we are talking about billions of litigation and stop of trading and things like that, that could have been probably mitigated or reduced considerably if they had some kind of monitoring operational system like the one we are proposing here. So DAMSat is actually based mainly on satellite image that we can process automatically, and then understand better the behavior of the dam. There is some components of artificial intelligence as well embedded there, because some of the movement that you will see in the dams could be expected, and there is a process of learning how each dam behaves. Basically, what we have there is different modules. We don't have time today to enter into too much technical depth in all of them, but we can combine satellite image with sensors inside and then put them all together. Some of these process and calculations we do are automatically, but others can be supervised by a technical experts, dam engineers, or things like that. And what it helps you, it's actually to be monitoring more frequently those dams, because you will be doing every day or every hour, depending on the frequency you're loading the data, and then it will raise alerts, and then experts can go and check those dams specifically, maybe go on a site visit if there is time to do so, but it keeps you on top of the game. Then all of these things are also connected to emergency planning tools. So the emergency planning responsible people can make decisions or understand the impact if that happens. For example, this is a hydraulic simulation of this Brumadinho dam, where we've got also a life safety model, so that simulates the behavior of people around and how they navigate and move around when they see the presence of water. And the study one of my colleagues did about the Brumadinho dam, it was really impactful, because it said that in just a 15-minute warning about the movements of the dam could have saved the 270 lives. Okay, so in some cases, just a very little warning could help people to evacuate and reach safe places, and then you can really avoid this tragic loss of life. Okay, so just to let you know, this is not a research project. Actually, this is a real commercial software available. We've created the first application. It was in Peru, where we are monitoring 31 dams in the Peruvian Andes, and it's been a great success. We are trying to extend this application in other countries. So if wherever you work, tiling dams especially, they've got a worse track record than water dams. If you see that there is the possibility of using this technology, please contact me or my colleague Tim Hurst, which is the Damsat business manager, and we will be very happy to let you know more about the technical aspects of this option. I'm going to move on to the other case. This is not kind of like a tool we developed for a specific project with UKWP-DBT, and it was in Yemen. The problem here in Yemen basically was that we all know that in Yemen there is always water scarcity, and population really relies for agricultural purposes, relies on groundwater for irrigation of fields and for water supply, and it's been really a problem. The droughts there have been consistent, with the difficulty added that the conflict that is happening now in Yemen prevents anyone to go there and take measurements inside of groundwater levels, and then it's really difficult to make any operational decisions on how to help these people, because we don't even know what's the situation on the ground. So it is impossible to send experts now on the ground because it's too dangerous. So what we proposed here was to create a tool that could be helping calculating what is the situation by using remote sensor data, satellite images. So what we did is we did an analysis of historical Earth observation data set from 2009 to 2021, and we've created a website where we are displaying all this data and calculating, estimating what is the groundwater recharge and what is the situation with these aquifers. We've put all together in a web portal, so stakeholders involved in these projects or making decisions in this country can see all the information in a central hub. And then we try to keep it very simple, but still very informative, and helping those that need to make decisions, have a central source of truth as much as we can now. No? Obviously, the key advantage is free available, so all the sets of data we've used in satellites are freely available, and that they have enough good resolution and very good coverage. The limitation that the tool has, obviously, is that we haven't been able to validate some of the results from these hydrological models and the ground-based data, and there are some uncertainties in what is the accuracy of what we are showing there. But I think anyway, it's a very good guess and better than not having any data. So I'm going to show you very quickly how the tool works. I think you can actually go to this website and you could see it by yourself. You just need to register by this. It is accessible for anyone. And the way it works, it's actually very simple. So you've got a map where you can actually select your data on interest on the left-hand side, and you can see different years where you want to see the data for, and then you can click in the map and you've got some contextual information, graphs, and other information that could be useful for you. So if you need to do any project or you need to make any decision related to groundwater resources in Yemen, this could be a very useful starting point. And again, this project obviously had a difficulty on setting up these tools and putting everything together, but it will be a very easy replicable tool in other parts of the world where maybe this type of satellite analysis could be very useful because of lack of access or because of large areas where maybe it is impossible to sample all the points. So maybe we could calibrate in some areas and then compare to extrapolate those results from the models to other areas. Okay, so if you think that this could be useful in any place of the world, feel free to contact me again, or Andy Ball, which is my colleague that is the expert on that topic. And we will be very delighted to let you know more about the technical aspects of this project. And I think that's everything from me, Maya. I'm not sure if anyone has any questions.
Wonderful, thank you very much. Yeah, we'll hand over. If anyone has any questions, again, please raise your hand or you can pop them in the Q&A chat. Okay, I've got a question from Steph. You just, there we go. Yeah, go for it, Steph.
Thanks, Maya. Hi, Juan. Great presentation. Thank you. I was just wondering, from a very obviously new to water perspective, what are the biggest threats to dams? Like when you're monitoring dams, sorry for taking it back to basics, what are the biggest things you're looking out for? Yeah.
Well, the first thing you would like to look is, do you see or can you see from satellite image any indicators of leakage? If the dams are losing water, that's actually quite dangerous, because then you can have some type of failure that are piping, eroding the dam and then failing. So we look in satellite images indicators that could show whether there is any increase or any leakage around those dams. Then if we look for movements in the dams, especially when they are made of earth, of materials that might move depending on the hydraulic loads and other things. So it could be expected that they move, but you need to learn how much they can move in which conditions, obviously, if the water goes up or tidal effects or things like that. So we look at that, and we compare satellite image in the way they move also with sensors on site. We've got some hydrological forecast tools, so we could predict how much is going to increase the level in that dam because of rainfall, and that could also give us some indicators of possible problems. And then the tiling beach is the area before the water gets into the higher level of the dam in tiling dams. And then looking at the profile of that beach is very useful, because it could be very dangerous if the tiling dam reduces too much. I'm not an expert in that, but this is more or less. So there are things that you can see very well from satellite images, this profile of the beach, and see how it's evolving over time. Okay, so these are the kind of things that you are looking at. And then if you find something that is quite dangerous or something you should be worried, is when you then automatically connect all these emergency planning tools to indicate what would be the impact of that failure. And the impact is not easy to calculate, because the key thing on dam bridge for this type of dam is the evolution of the bridge, because it is not so. For example, in concrete dam, it's a sudden break, so it's very easy to calculate. Just the dam suddenly is not there. But in tailing dams and in earth embankments, it is the process of how this hole starts to increase and makes bigger, and that is going to be controlling the discharge of water. So we've got some modules that calculate this type of failure. It is based on the type of construction of the dam, the materials inside, and there are some models that we use to calculate that. And this is very, very important, because it will affect the flows that then you can put into a hydraulic model and calculate the flood extent. And then if you got population, it's not the same as a dam that fails in a place where there is nobody. Maybe you don't care, or if it's nearby any population or things like that. So do people have the possibility do they have escape routes where they can go and things like that? And that's again the warning time, how important it is, the warning time for minimizing any casualties in that case. No? So yeah, a lot of components. Ideally, you would like to see them all together in one place. Again, all these web tools are very helpful by putting everything into a central hub. And different stakeholders could be seeing it simultaneously, and then it also facilitates the communication between different stakeholders, sharing the same data and looking at the same screen and the same graphs and models. Yeah.
Sure, thank you. And are there other dam monitoring technologies out there, or is this a kind of like leading technology from HR Wallingford?
I think there are a lot of well, there is a lot of history and a lot of tradition in monitoring dams with equipment on site. So sensors that analyze this and people doing clever things, artificial intelligence, looking at the movements.
Yeah.
They rely a lot on site inspections. So dam engineers need to go and see it. So this is a way of kind of doing site inspection automatically in large extensions very quickly. But obviously it doesn't replace that. You should carry on doing your general inspections more in detail on site, but it helps you to be on top of the game and not suddenly arrive there and say, oh, there are some cracks, or even not arrive there and it collapses before you go and inspect it. No? So there is a lot of technology there, but I think this is probably one of the first one, if not the first one, it was the first one, I'm sure, that it was used in satellite image applied specifically to dam safety. So this is unique in this sense, yeah.
Good to know.
We do have, I think if people want to know more about this, there is a website as well, damsat.com, where we explain more in depth all the details of the different modules, and there are nice pictures and animation, I guess, as well. Yeah.
Excellent.
Great, thank you. Are there any other questions from anyone else at all? No. And so we did have a question submitted online before, and it's just sort of saying, how do you see AI further contributing to dam monitoring in the future? So you're saying that obviously this satellite images in dam safety is quite a new thing. How do you sort of see that developing over the next few years?
Yeah, that's a good question. I think AI is going to change everything we do in many aspects. So dam safety is not going to be an exception on that. And it's really important because it helps you to discard maybe false alarms and look at some things. If you got just static trigger values, you might be raising false alarms and people might get fed up of your system. So by understanding better, when something is problematic or not, or the other way around, maybe data that doesn't look problematic based on experience, it can be analyzed better. I think it's very useful. It's in a way going to help us to pass what before was experience and gut feeling of people and the kind of analytical eye of an expert saying, oh, this is like this. In a way, we are streamlining and we can do maybe not to the same extent with the same precision, but fairly close and helping us to make and understand better the processes, that especially when they are extremely complex and with multiple variables and things like that. So I think it's an essential tool, and it's going to be more and more important in the near future. Yeah. You are mute, Maya. We cannot hear you.
Sorry. Thanks. Yeah, thank you very much for that. I think we'll just give people a couple of minutes if they're joining for the next session before we move on.
Great. Thanks.
Okay, I think we're ready to make a start again. And so it's got you again, Juan, again on digital tools for resilience. I hand over to you. Thanks.
Thank you. I'll take control again so I can move around. So yeah, hello again to everybody. I'm going to talk about a different type of set of tools that we've developed in HR Wallingford. And the idea here is to help water companies to become more efficient, especially when tackling water leakage. So we've got this tool called Simon Water, which is commercially available already. And I'm going to show you a little bit what it is about. We are still developing and what is in the pipeline in terms of development. I don't think we need to state why tackling water leakage is important. We all know that water is a very scarce resource, and losing water, it has a monetary and environmental cost. Because for all this water is drinkable water, potable water, so it's something that we've treated, that we've pumped it. So there is a lot of waste of energy whenever we are losing any liter of water. And obviously also we are increasing our CO2 footprint because of this consumption of energy and resources. So losing water, and there might be other reasons, maybe I'm forgetting here, but losing water is a bad business. Everybody knows that. And we need to do our best to reduce that and minimize that. So why it's so difficult? Obviously, water supply networks are underground, are difficult to see. It's not that obvious where leakage are. And unfortunately, there are no magic ones. Okay, so the tool I'm going to show you now is not going to fix all the problems magically of a company. It's just going to be an additional tool in their tool set that will help them to become more efficient. But they really need to make an effort. And basically, it goes down to send people on the ground and trying to locate those leakages. So it's doable. We've seen many examples all over the world where a leakage can be reduced, but because of this manpower on the ground, it's time consuming. It is actually very expensive. And any tool that you can have, any strategy, anything that helps you to plan this and to be on top of the game and get resources on the right place at the right time is going to be essential for reducing the impact of these leakages. The bad news on this is it's a never-ending task. It doesn't matter how much you invest and your network is perfect. After a few years, they will start developing again because of the aging on the infrastructure. So having these strategies are very important because it's a never-ending. The war on leakage will never finish. It's going to be always there. Okay, so it's not a one-off effort, and then you can relax the rest of your life. Okay, so it is a complex business, definitely, and this is the reason why we try to provide with something to the water industry, Simon Water. So our tool is just divided in two modules. The first one is already commercially available. The second one is actually going to be hopefully available by the end of the summer. And we are trying to do some pilot studies with water companies all over the world. I will come back to that at the end of my presentation. The leakage detector, what it does, it helps you to manage your SCADA data, all the sensors that you've got in the network, and it helps you to do some statistical analysis. Depending on which area of your network, there are different methods, but it will tell you if an area in particular has some leakage by doing some type of estimation of water balance. Okay. Right now, in a lot of countries, there are a lot of deployment of smart meters. So this is also a technology that we have incorporated into our tool. So you can use just not the SCADA sensor that you got in the data flow sensor, but you could also put on top of these calculations any information you might have with the smart meters. The idea is once you've detected an area, a district meter area or a trunk main that has some problems, ideally, automatically, it will cascade down to module 2. And by using additional pressure sensors and hydraulic models, it will help you to narrow the area where that leakage is. So helping those teams on the ground, rather than having to visit a very large area, go to a much smaller area so they can try to identify and find it out, this leakage much quicker. Okay. So the idea of these tools is, again, web-based. So anyone in the company can use it, very easy, accessible, automatic. So this type of methodology that we are implementing here, especially the module 1, they are not rocket science. Everybody knows them, but the problem is they are time consuming, and water companies, they don't do it in all their district meter areas every single day. So this will help us to streamline that and get more information. it is practical, easy to use and install, and it's affordable. I was criticized the other day to say affordable, but I truly believe that it's a tool that is actually quite cheap, actually. I'm going to show you some screenshots of these tools. So what you've got is, in this case, is a different district meter areas, this different area where we can do balances of water in and out and estimate it. So what you can have is you've got different indicators there. You could put the total leakage in liters per second, or you could do leakage per kilometer of network, or leakage per consumer, per client, or use the international leakage index. So there are different indicators that you could use to prioritize them, and then you could see which one is the worst one, and then you can maybe send your teams there and have a look at that. Okay, we do also have our own index, which is new leakage appearing. Our tool is very focused not so much in detecting historical leakage, but to help you to detect very quickly those new ones that are happening. If you look into trunk mains, into the transport of water into different from one area to another one, so the software also can deal with that and can do a different type of analysis, which in this case is much balanced and minimal night flow. What's the idea? The idea is to create some estimation of what the leakage is. And I'm saying estimation because this value is never going to be 100% accurate. It's going to be always based on some type of estimation, because there are a lot of uncertainties. For example, we don't really know the real consumption of our clients in real time. So there are a lot of uncertainties. So this estimation is going to be always wrong. But the important thing is to see the trends. And that's why it's so important to do it every single day in every single location. By seeing here the trends, you can see, for example, in this example, it oscillates around some kind of value, and suddenly it ramps up and it goes bananas, it goes up into the sky. Okay, so this is a leakage. It's been detected there. There's a change in the trend. This is not a problem of my estimation being wrong. This is something happening. And then what you can do is identify that very quickly. It's not something that you identify at the end of the year when you do the balancing of your billing against the water consumption. You identify it in 1 week less because you see the trend, and then you can send the teams there and they can fix it. And in this tool as well, you will see how much or how well it's been fixed. You can see that here they fixed something, it went to a better level, but not much, then they fix it again. And then it went in 2 steps down and eventually didn't reach even the same level it was before. So maybe they didn't detect the right leakage, they found something else, but you can see always what is your past history and your best performance state, and you could aim for that with this tool by looking at this information. So the tool is very flexible. It brings all the data inside of a single hub platform, and you can visualize all your flow data. You can look at false alarms because of unusual consumption. So it is really complete. But the point that we are really excited about is this new module 2, which it will help you to locate where that leakage is inside of the DMA. So this network that you see here is about 65 kilometers of a network. This is a real case where we tested with an Italian water company, doing some tests that they were opening hydrants in the middle of the night without telling us, and we were looking at the data and analyzing it and telling them where we thought the leakage was. So it was a bit of a hide and seek exercise, and it was really successful. So in this 65 kilometers, for example, we narrow it to something like 4.6 kilometers. Okay, so you are narrowing more than 90% the area in which you need to look at it. Okay, so that's really, really exciting, and we think it's a methodology that works really well. Obviously, you need more data. You need to have also pressure sensors scattered around the system, and you need to have hydraulic models that are calibrated and with quality. So it might not be applicable in every place of the world, or it will require some pre-work to get this information. But if you can do that effort, then you've got a tool that could be very useful. And that comes up with my final slide here. So we already have some commercial users in different locations of the world, but we've done pilots where we've tested this, especially with the module 1, the leakage detector. But now we are entering this phase 2, the leakage locator, which is very exciting. And we are looking for water supply companies all over the world that they might want to participate in a free of charge pilot study to test it. So we've got some ongoing already projects in Italy. And we've done something in the UK. We are doing something in the UK now with UKWP, where we are using also our tool to analyze the impact that smart meter data could have in those systems and how we can use it, smart meter data, to detect things faster. So we've got also something going on in the UK in this sense. But I am really traveling today to Argentina to talk with a company there to do a pilot of this tool. And we have some 2 ongoings in Hong Kong and in Thailand, plus other places where we've got early discussions about how to do that. So my call here is anyone watching this that is in a place where obviously you've got leakage and water scarcity, and the water company is interested to try something else or something new with no cost to them apart from their time and setting up their servers and things like that to do it. That I would be delighted to hear from you, because I think this is a tool that could be very, very helpful for them, and it will make them more aware of even problems that they don't have, and you know, it will be using their SCADA data, which a lot of time they got there and they don't really know what to do with that data. Very expensive to implement, and a lot of time is not optimized, it's not used as much as it could be. And this type of tools always helps you to get them out the most of it. Okay. I'm divagating. Maya, stop me. So I think this is a good time for stopping and checking whether there are any questions. So, yep.
Great, thank you. Yes, so as you say, any questions, please do raise your hand or put them in the chat.
If no one has a question, I'll jump in again. This is more of like a kind of theoretical question, I guess, about leakage in general. I've heard a lot about people saying that leakage is inevitable and we need to manage it better. But do you think there's a way that we can build systems in places where we're building new cities and starting from scratch? Is it possible to build water systems without leakage, or do you think it's an inevitable part of?
I think it's inevitable. You will always have leakage. The countries where they minimize the leakage, like Japan, it's because they are inspecting more frequently, and they are doing, obviously they are very strict in the way they build. The better you build, the less likely you will have, and the more you are postponing those leakage problems. But eventually they will always happen, and it's a matter of investing money and time to detect them quicker enough. So these type of tools help you to do that. It's not going to avoid or is going to reduce the presence of leakage. The only thing is helping you to find them out quicker, so you can act and prioritize where you look at in terms of the areas, and then hopefully in terms of the exact location, so you can move on to the next one. But leakage are going to be always there. It's going to be impossible to not do it. Obviously, if you build with better standards and you put more care, especially in the joints of pipes and things like that, you might be able to reduce them and postpone them, but eventually they will always appear. Sure. One of the pilots we are going to do in Thailand is actually a new development for scratch. Hopefully, we will see that at day 0, they won't have any leakage, but I suspect that we will see that there will be some leakage even from day 0 if they haven't built it correctly. But the idea is this: someone starting from scratch, which is the ideal situation, hopefully with leakage 0, and monitoring from day 1 and seeing any change on that one, and then being able to replace it very quickly. So now it's a small island in Phuket where they are going to build this system. I'm looking forward for the site visit. I'm not sure if they will invite me there, but yeah, it is very exciting, because usually you deal with network already with a lot of problems. Some of the places where I'm seeing 50% of leakage, you can have 50 or 60% of leakage in the system. So, you know, for every liter of water you put and you treat, you lose half a liter. No? It's amazing.
Great, thank you. I think we've got time for one more question. Are you able to sort of explain a bit more about the outcomes of those pilot studies that you have done?
So far, what we've seen with people doing these pilots is, obviously they haven't been long enough to draw permanent conclusions. But first of all, it helps the water utilities to understand better their data. Every time that you do an exercise where you are using your data, massaging, and trying to understand what is going on, it really helps you. A lot of time they realize that they didn't know the magnitude of their problems and that they didn't really know what was going on. So they were living in the ignorance and that's the reason maybe they were so relaxed. So every time that you try to understand data, it will help you to perform better, because you will see better things that you don't have. So they always find it useful in that sense. And then obviously they've seen that it helps them to prioritize. A lot of time they don't have the resources to tackle all those problems. That's a secondary problem. So they get overwhelmed by seeing all the problems and not having enough resources to send them there. But hopefully that's where we put also as well the module 2. If we can narrow the areas where they look at, they will be more efficient. They will be more efficient solving those problems, and they could move on to the next problem in the waiting list quicker. So the feedback so far is very positive. People using it, and especially because it raises the awareness of problems and situations that they didn't even know about.
And is this something you can or hoping to use in water companies rather than potentially government-led programs?
Yeah, well, it needs to be the owner or the person that is responsible for fixing those leakages. Is the owner of the assets that need to. We see that they need to use this. It would be great if government say this is something compulsory. You should have this system like you have in another industry where there are some laws that say you need to have this safety mechanism or these indicators, no, to help you manage things better. But it needs to be the water company, the people that manage the network, and because these are the ones that go there and fix things, no? So if the government, first of all, they might not have the data to build this, they might not have access to the SCADA data or the pipe information to run these models. So it's the water company. But obviously government can push for this type of things, or maybe give grants to do these preliminary studies or pilot studies and facilitate the implementation of some of these tools.
Great. Well, thank you very much.
Thanks to you.
I think we have a couple minutes before our next session starts, and it will just again allow people to join from the red room. So we'll start again in the next couple of minutes. Thank you.
Thank you. Bye-bye.
I think we'll move on to our next module. So we're looking at managing resilient systems, and we have Tom Sangster with us looking at the preventive management of critical infrastructure. So welcome, Tom.
Thank you, Maya, and hello, everybody. Maya, can I take control and control the slides myself?
Yeah, of course, of course.
Thank you. My name is Tom Sangster. I'm the director of Downley Consultants, and Downley Consultants is a small specialist civil engineering consultancy. We are a small team of very experienced specialists in the whole area of underground network pipe asset management, water, wastewater, gas, some industrial, and some mining applications. A large part of what we do is condition assessment. So I'm going to use one particular case study of a gravity sewer to show the condition assessment process that goes through from understanding a problem to coming up with a solution. It's something we do a lot of the time. This example is gravity sewer. As I say, the general principle that we're showing here applies to all underground pipe networks, water, sewers, and the big nightmare for many people, the pressure sewers, the rising mains or force mains, depending on the terminology you use. So we are hands-on engineers. We like to get hold of problems and solve them, rather than taking a lot of big picture views, but there is some big picture. You need to understand risk management and risk assessment as part of this whole condition assessment process. So we'll look at what the process is, and it's essentially a series of steps. There's a great temptation, and unfortunately many people give in to the temptation to jump straight to a solution. When they have a problem, they jump straight to the solution. They know what the solution is before they've really understood the problem. And that usually just creates more problems. Either it doesn't solve the problem, it's a complete failure, but it doesn't solve the problem, and you're back to square one having spent a lot of money. So we go through a process. We'll start with a data audit, look at what we already know. What's the history? What's the original specification? Do we have drawings? What do we know about the pipeline? Material size, operational history, all of those things. To begin to build a picture, and already then we can start to understand some of what's going on and some of what might be necessary to restore the performance of the pipeline, which is really what we're trying to do. We always talk about condition assessment and improving the condition, but the reality is what it's all about for the client is the performance. And you want to restore that performance to the serviceability level that that client needs to operate at, and at the risk level that that client is comfortable operating at. The risk assessment is important. That goes on at this stage as well. All of the condition assessment work that we do essentially initially identifies and then addresses the likelihood of an occurrence, say a failure. That needs to be put alongside the consequence of a failure. And we'll see for the particular case study we're going to see that was how we arrived at the solution, or the eventual option was taking into account consequence of failure and the level of failure that this particular client was, the level of risk, sorry, that this particular client was happy to operate at, which was a very low level. They wanted a very, very safe solution. So once we've done this initial audit, part of the risk assessment, we can then understand what we don't know and what we still need to find out. And that's where inspection comes in. Again, there's a temptation to rush into inspection. Inspection is expensive, it's disruptive, so as little as possible, as much as necessary. We don't need 100% perfect information. Smart engineers can fill the gaps in themselves from their own experience and engineering knowledge. Once we've done the inspection, then we're in a position to do the full condition assessment. We have input data from our data audit, we have data from inspection, we can make the assessment. And it's important also to stress the difference between inspection and assessment. Many people think it's the same thing. It's not. Inspection is acquiring data for somebody to then assess and understand. And I often liken it to if you have a heart problem and you go and get an electrocardiograph done, that's inspection. The output from that is those very familiar squiggly lines that we see of the heartbeat. They would mean nothing to me and possibly to you as a layman, but an experienced cardiologist can look at that, can interpret it from the shape, the height of the relative parts of the signal, the distance between them, the length of them, can interpret that and understand whether that heart has a problem or what that problem is. And that is exactly the way we work. We work with inspection data, and we take that and we interpret it from our knowledge to get an understanding of what it's telling us. And that's the core of the assessment process, if you like. And then we can move on to the solutions. So we'll look at one particular case study. This is in Saudi Arabia. Major trunk sewer in the centre of a city, served a large area, including the area where all the government ministries are. And this could be, quite frankly, any large city anywhere in the world. You have the very big sewers. They're the biggest, they're the deepest things under the ground, unless you're a metro system. They tend to run below major highways, as in this case, across several intersections. This one was unusual. We'll see in a moment a diagram, because it was located immediately below a very large rectangular stormwater culvert. Failure would be catastrophic. That was very clear. So very high consequence of failure, very high value in knowing the likelihood of failure. We had some information on the pipe, on the length. It's about 5 kilometers in total, the diameters, the materials, and we had some more information from the original drawings of wall thickness, so we knew that we could reverse design and understand how we stood in relation to loadings. But the location, our sewer, is the circular one at the bottom there. But above it, we have this large stormwater culvert. So we have two very different loading conditions. When that culvert is empty, really it's not transmitting any load, any surface load to the sewer, because it essentially bridges across it. When it's full, there's a lot of load on the sewer. So we had to understand that and take that into account. And also in practical terms, the access to the sewer is from the culvert. The manholes in the sewer, the manhole covers are in that culvert. So all the work has to be done in the culvert. Potentially big safety issues. You don't work when it's raining because you can't get out quick enough. So there were some special conditions here. We needed to inspect that sewer, and we chose combination method. So for our inspection data, we worked with a system of CCTV camera, which you nearly always put into a sewer, but it gives you visual data, nothing much you can measure, together with a laser scanner. Now that does scan and gives you digital measurable data. You can measure corrosion in a pipe. And remember here, we have reinforced concrete and mainly asbestos cement pipes, so cementitious material. And then this also has sonar. We couldn't get the sewer empty. Excuse me. So we needed sonar to understand a little about what was going on below the surface. This is typical of the sort of output we were getting. You can see in the photograph at the top right, very corroded in the top half of the sewer. The bit was never full or very rarely full. This sewer generally ran about half full, but very, very slow flow. So quite septic conditions, hydrogen sulfide being generated, which then attacks the concrete as sulfuric acid. So we can see significant corrosion. The top left of the diagram, you can see the laser data we were able to measure. And we can see in some places, this particular one, 42 millimeters of wall loss. So we had to take that into account in our calculations. How safe is this? How much light does it have left? What do we need to do? And so you can also get a development of the pipe. So the part across the bottom of the diagram is essentially the center line of that horizontally is the invert of the pipe, and then it's opened out, if you like, by as if it had been cut along its crown. And the yellow and the blue are the spring lines, and that's where we were seeing quite a lot of corrosion. So and we were seeing some information from sonar underneath the water, but not a great deal. That wasn't particularly successful. So we had much less quality of information as to what was going on below the waterline. So we take that, excuse me, again, we take that, we assess it. This is an example of the sort of Bayesian algebra approach of lots of different inputs. It's evolved a bit since then, but the principle is the same. You have systems for assessing and putting weightings on different factors, be they structural, be they hydraulic, and you come through to understanding a level of risk based on the condition of the asset. So we've said already in terms of risk assessment, high consequence of failure, we need to know the likelihood of the failure and then to minimize that, keep that down at a level that enables the utility to operate without more risk than they're happy to take. This is part of the outputs. On the left, we're looking at what's the minimum wall thickness for the asbestos cement pipe at different diameters when the culvert is full of water. So that's the maximum external loading condition. And on the right, that's just one example of some of the analysis. And on the right, you see a very simplified version of the final output. We split the line by material and diameter and assigned risk levels. And then this is a sort of simplified low, medium, and high risk. As you can see, the 2 meter diameter reinforced concrete was all low risk. There's a lot of very high risk in the larger diameter parts of the asbestos cement pipe. So now we're able to see and begin to prioritize, understand the scale of the problem. Behind this, which you can't see on this slide, it is looking at the distribution. Are all the problems concentrated in one part of the pipe? In this particular case, they were fairly well distributed along the whole length. So that again pointed us towards certain solutions. So at the end, we come to some options. And these were the options we were able to suggest to the client. Going from the top, a full structural rehabilitation of the asbestos cement pipes, and then joint sealing in the 2 meter reinforced concrete pipe. There was no structural need there, but possibly joint sealing to stop infiltration, which we'd been able to see on the camera inspection. Alternatively, a bit less rehabilitation, full structural on the 1700 millimeter, partial on the 1400 and 1200. That means just lining the really bad bits, but not all of it. And then again, joint sealing in the larger reinforced concrete pipe. Maintenance and monitoring, carry on just maintaining it, monitoring it, patch it up, keep it as it goes. Always a viable alternative. Further investigation. It's very easy to keep wanting further investigation. All we need to investigate more, then we can make a better decision. Eventually, you have perfect information, it's cost you a fortune. So the cost of that additional information very quickly becomes greater than its benefit. There's a point at which you have to stop and start applying your engineering knowledge. And then there's always the do nothing option. It's not one we recommend, but it's always there if that's what the client wants to do. So the eventual recommendation, we also costed all of these options, of course, to look at their cost implications over time. And the eventual solution that proposed and agreed with the client was the safest one. Full structural rehabilitation of the asbestos cement pipes, joint sealing in the reinforced concrete pipe. That was the one they agreed on. The method we proposed to them was to use a spiral lining, this with a growted annulus. This is a PVC profile strip, structurally designed, that can be put together in a spiral in this sort of revolving cage, and spirals out into the pipe, leaving an annular space, and that annular space then when it's finished is growted. It's a fully structural rehabilitation. It's especially well suited to these larger diameters. It's especially well suited to sewers where you can't get them dry for cured in place pipe, which is not a great solution at these diameters anyway. But the other great advantage of it was, remember, all of the installation work would have to be done from within that stormwater culvert. And with this, if the rain suddenly starts and that culvert starts to fill up, you can just stop and leave it. Get out and you can come back. You can't do that with cured in place pipe because it'll carry on curing and you end up with that half done, half cured, half finished job that you've essentially got to rip out and try and start again. So there were some practicalities there as well that drove us to that solution. So that's just one example, as I say, of the process, the thinking, the thought process that involves inspection as well as data audit to provide us as experienced engineers in this field with a means of coming up with cost-effective solutions for the client. This is a gravity sewer. Very different in water mains, very different even in pressure sewers. You need different inspection methods, and you're looking at different types of problems. Obviously, you're dealing with pressure inside the pipe, but the general principle of working through condition assessment to be cost effective and come up with rehabilitation solutions and risk analysis and restoring the performance of the asset is consistent across all of those. And that's the end of my presentation, and I'll be happy to take any questions.
Great, thank you very much, Tom. So yes, any questions, please do raise your hand or pop them in the chat. We do have a question that was submitted beforehand about sort of the costs and how sewer repairs are quite expensive. And if you could potentially talk about the feasibility of doing this, potentially with, you know, the ageing infrastructure of the UK in particular.
Yes, sewer repairs can be expensive, no doubt about that. But when we look at repairs like this, where your alternative, the ultimate alternative is to dig it up and replace it. As a general rule of thumb, when you're doing that, 75% of the cost is to make a hole and fill it up again, and only 25% is what you actually do when you're down there. More recently, people have postulated that same ratio applies in terms of the CO2 footprint. Most of that comes from digging and backfilling the hole and bringing in material and taking material away. So both in cost terms and environmental impact terms, there are great advantages to being able to repair and rehabilitate the existing asset. And you know, my feeling is that the asset is actually the hole. It's the space inside the pipe, not the pipe itself. And if we manage the pipe itself properly, we can give that asset an almost infinite lifetime. And that's always the cost-effective way to go. You can't always do it. There are situations where you've got such a complete failure of a line, there's not much you can do with it other than replace it. But that may be abandon it and replace it offline with a microtunnel solution, for example. So yeah, there are always those options, but on really aging infrastructure, which lots of cities have, we have in the UK, many other parts of the world, increasing pressure on them with urbanisation, it's not a feasible option to replace them in many cases because of the disruption, the size, the depth. And these trenchless options now, if you choose the right one, you go through this process and don't just grab the first one that comes along, you can get a very, very cost-effective solution. With a service life, we tend to work on 50 years, but they are actually longer. And you can go back and in 50 years' time, there'll be new technologies or the same ones again, and you can maintain this asset over a very, very long period of time.
Great, thank you very much, Tom. Thank you. And yeah, if anyone has any questions, you can always reach out to Tom, I'm sure, at a later date. Great.
Please do.
Thank you very much. Thanks, Tom.
Thank you.
Okay, so continuing with managing resilient systems. Bear with me one moment just while I get the PowerPoint back up. And just pass back to where we are. Right. Wonderful. So next up, we have Justine talking to us about demand management. Welcome, Justine.
Can we go to the next slide, please?
Yeah, of course.
So hi everyone, I'm Justine Leadbetter, Senior Consultant at WRC, heading up the leakage and water resources area. And I'm going to talk to you about non-revenue water and some of the capabilities that we have at WRC. Next slide, please. WRC is a consultancy based in Swindon in the UK. The company was originally formed in 1927 and was a government agency until the UK water industry privatised. We cover a wide range of topics, but tend to focus on research to solve water and environmental sector-wide issues. And we have a range of technical experts and physical testing facilities to support our research, as well as a library of data and research that we can draw upon to drive improvements. So we're constantly looking for new ways to innovate and make a difference, for example, using machine learning and data science techniques. Next slide. So WRC has a really rich history in non-revenue water management. In fact, our managing director and two of our other directors all have a leakage background, as well as numerous others around the company. So this has resulted in our involvement in projects with a wide range of drivers. We frequently contribute to industry-leading research, such as the Water UK route maps. We've done this both for leakage and for consumption. And we have experience both here in the UK and internationally. So, for example, we're currently doing some work in Oman and earlier this year in Brazil. Additionally, we frequently provide strategic and tactical advice for non-revenue water management. We support regulators and contribute to standards and guidelines. But what's a bit different is WRC also operates a collaborative research programme where companies can come together and fund a piece of research as part of a portfolio project. So this is one of the key ways that we can promote and contribute to innovation and learning across the sector. And kind of recent NRW projects have included research on ultra low loss new networks. And then finally, because WRC has a fieldwork part of the business called technical services, we're able to join together both the data side of non-revenue water management and also the fieldwork side to allow for data-driven NRW investigations. And this is an example that I'll expand upon now. So one of the key problems when managing non-revenue water is trying to differentiate between real and apparent losses. So those losses that are physical leakage and those that appear to be losses, but it's actually due to meter error or meter under registration. And this is what we've tackled in our upstream losses programme, which we've delivered for numerous water companies. This focuses on losses upstream of DMAs. However, the theory can be applied throughout the network. So we created flow balances for discrete areas, looking at water in versus water out, considering that systematic meter error. And then from the analysis of this data, we were able to indicate whether there is a real or an apparent loss, and then recommend a prioritised list of interventions out the back of it, which could range from meter verification to try and reduce the error and reduce under registration all the way through to mains renewal. And then depending on the recommendation, we can then work with our fieldwork teams to enact these interventions, for example, through leakage detection surveys, condition assessments and meter verification. So following this method, we can identify the quick wins, both in real and apparent losses. So in this case study, we produced over 600 balances over 6 months, producing intervention recommendations for the assets in each of these areas. So for example, we were able to identify 2 megalitres per day of physical losses on a single section of trunk main and then validate this by inspection. So the project made the most of all data sources available. Obviously, the more data you have, the more confident you can have. So we could maximise our insights and increase our confidence in the recommendations that we were providing. And so we were pulling from flow data, meter asset data and the relevant meter performance data, reservoir level data, repair history, GIS asset location data, and network schematics as well. Could we jump to the next slide, please? So this is what we produced for each balance area. So interpreting the graphs allow us to indicate whether the losses seen are real or apparent, or whether there's actually unmetered consumption instead, and so that's what's causing the gap in the water balance. But then all of the recommendations are put within the table below, along with an indicative cost to aid in strategic decision making. So overall, this allows for a holistic approach for reducing non-revenue water using both data and fieldwork-led approaches, and it can be used as an iterative process to drive continued improvements from data production and management through to physical leakage identification. So once you've finished it, we can you go out, you do a number of the interventions, you can then rerun the balances and go through the process again. So it's a really great way to just have continued improvement. Okay, thank you.
Great, thank you very much, Justine. Yes, if anyone has any questions, please do raise your hand. I've got one. Maybe you could talk about some of the challenges that you face, like what might be the biggest challenges that you've experienced.
So I think when doing this, the biggest challenge is normally the data side of things. Okay. It's trying to get all of the data in, because obviously data quality is such a key part of this. If you don't have confidence in the data quality, then you don't really know if what the output is going to be is that you don't have the level of confidence that you'd like. So there's a lot of data cleaning, a lot of data flagging, and that side of things before you can even get to producing anything. And also just with the number of different data sets, it's do they align? So it could be that in the GIS there's a meter, it shows that there's a meter, but then on a schematic there isn't a meter, and then we can't find flow data for it, and so you don't know if there actually is a meter or if there isn't a meter. So then we need to get the field team out to go and confirm whether there is or isn't one, and then if there is, we need to then try and work out where the data is for that meter, so we can then put that into the balance. So yeah, it can be quite a long process to build confidence in the balance areas to begin with, but once you're there and they're built, then you can just keep reusing them and reusing them as you do the interventions. So it's well worth putting the time in at the beginning to make sure you do have that level of confidence you need.
Great, thank you. I don't know if we have any more questions at the moment, but I'm sure people can reach out to you. You've put your email on that. Well, thank you very much for your presentation.
Thank you.
So that is all for our modules today. Thank you all for joining. I will just reiterate, if you're able to fill out the feedback form, that would be great. It'd be really nice to hear your thoughts on how we did following the UKWP and DBT LinkedIn pages. And that is all from me today. I hope you've found this session insightful. Thanks very much.